Good afternoon and welcome to yet another asset session here. We have a pleasure of having Dr. Ashish Mahabal here. He's a Deputy Director, Center of Data-Driven at the Data-Driven Discovery at Caltech, USA, and adjunct faculty at IUCAA in India. He received his PhD at IUCAA in 1998, and after a break postdoc at PRL, he has been to Caltech since 1999, and he has been the chair of Astroinformatics and Astrostatistics Commission of the IAU. Currently leads machine learning ML for the ZTF survey and ML for Roman's rapid team. In recent years, he has extended this expertise in years of expertise in ML and AI to medical data and other areas like microorganisms. On a personal research level, he is interested in variable astronomical objects, classification of all kinds, and outreach. He led the development of Zarth, a game like Pokemon Go, but for astronomy. So, as he is very popular in that field as well as in other things. And he writes popular articles on astronomy and society, and he's published science fiction author as well in English as well as in Marathi. So it's nice to have you here.
Thank you so much. Can you hear me? Okay, perfect. Yeah. Okay. So as Parag said, my name is Ashish Mahabal. I'm at Caltech. I'm the Deputy Director of the Center for Data-Driven Discovery. So the Data-Driven Discovery Center does all kinds of data science things. So my PhD is in astronomy, but for the last 10, 12 years, I've been doing some data science related things in medical data as well. And one of the things I'm interested in is transfer learning from one field to another. There are very interesting methodologies that can be taken from one area to another area. So if we have time later on, we'll talk about it. But also during this talk, if you have any questions, please stop me whenever you want to, because I would like this to be more interactive if possible. Also, since yesterday, I have had discussions with many students already on one topic or another, and based on that, I have inserted a few slides here and there. So it's like a combination of multiple talks. So again, we can go into details of any of those either during the talk or later on as well. So this is the broad outline of my talk. What I want to do is that mention how there are these different telescopes or surveys and how there is so much more that can be done if we bring elements of these together and how they work with each other. Not everyone is trying to use it that way. Many groups try to use their own surveys and take a little bit from other surveys, but there is much more that can be done with archival data. So for instance, I'll talk about the complementarity of ZTF, which is the Zwicky transient facility, the LSST Rubin, which is a very large survey from the Southern Hemisphere that started very recently, still commissioning, and Roman, which will be launched next year. So one of the things that one should think about is adapting brokers, because these surveys take a lot of data, and the primary purpose for which they get funded are taking the data, not necessarily making a lot of science from the data, which gets left to other people, collaborators, and so on. And one of the important things that is to be done is classifying the objects that they observe. So you take data, but then what are those data? What are the objects that are being represented? Because as you go fainter and fainter, or as you improve the cadence, you start looking at different aspects of the night sky, and then that reveals interesting facts. And those are the facts that can be revealed through such brokers, which essentially are classifying things. So many people for a long time have been interested in individual objects. That is how you drive the edge of the envelope. You look for the farthest galaxies, you look for the brightest supernovae, you look for this, you look for that. But what happens with these surveys is that you are now able to gather, say, tens of thousands of supernovae or thousands of exoplanets. And what that allows you to do is something along the lines of population level analysis. And once you have population analysis, then you can start looking for anomalies, things that are not part of those groups, that are not part of those clusters. And that really drives science in more interesting ways in some sense. Some of the things that we'll also look at are the lessons from ZTF, the gap analysis, because different groups, even within a survey, are interested in different sciences. And they try to look at the data in specific ways, but that creates a big multidimensional space, which leaves a large number of gaps. And what is it in those large gaps, again, can lead to more science. And that is where, again, bringing these different surveys together and trying to look at them in a combined way allows you to do an analysis of that kind. And again, as I said, if we have time, we can talk a little bit of cancers and fungi. Otherwise, we can talk about it later too. Okay, so some of the important factors are what is the coverage of a survey, what is the cadence, and how you can do characterizing with that particular survey. how is it that you can bring that into effect? So let's look at this. ZTF covers the North Hemisphere. It's based in at Palomar. It's a 48-inch telescope, 1.2 meters, and covers the entire northern sky at a depth of about 20.5 magnitudes or so. Whereas Rubin is in the south, but there is a healthy overlap between the two. So roughly minus 30 declination to plus 30 declination is where the two surveys overlap. So that's the area where both those data sets can be used. Roman, on the other hand, is going to be in the sky. So it can potentially observe the entire sky, but it's not going to be a sky survey in that sense. We'll talk a bit more about that. But the areas that it has surveys of do overlap with Rubin, and they're also very deep. So those are the different parameters, those are the different dimensions that you can start looking at. In fact, one of the earlier slides, this does show some of the surveys that Roman will be doing. Right, again, you can see that it doesn't cover the entire sky. So let's look at some of the unique features. ZTF has much better cadence than these other surveys. Already we have had more than 1,500 observations at almost each location in the entire northern sky. 1,500 is a large number. Compare that with, for instance, what LSST Rubin will do is that they will have 1,000 observations over 10 years in all filters combined. So ZTF already has more. Of course, the difference is in the depth. And the reason I'm also bringing in LSST Rubin is that there's interest here in Mumbai and India in general from the contributions that they will be doing for LSST Rubin later on. So ZTF, as I mentioned, goes to 20.5 magnitudes. And these two numbers indicate how you can get more from the survey, how you can get more from the data. Right now, we are implementing something called ZVAR, where some force photometry is being used that allows us to go to 22nd magnitude. So though individual images are 20.5 magnitudes, by force photometry, you can go to a couple magnitudes fainter. And another thing that we are doing right now is, in fact, aligning them in a more optimized way so that once you do stacking in that fashion and then do force photometry, you can go almost to 24th magnitude. So again, while one observation goes to 20.5 magnitude, every magnitude is 2.5 times. So clearly we are going several times fainter by combining the images and taking force photometry on that. And what we have with ZTF are the G, R, and I bands. But again, where ZTF ends, in some sense, LSST begins, because with LSST, a single image can go to 24th magnitude, right? So that is what we have. This is some more details of ZTF, for instance, that, as I said, it's a 1.2 meter telescope. A single image is 47 square degrees. It's huge that way, right? It's one of the largest fields that we have. And for comparison, the full moon is about a quarter square degree. So 200 full moons fit in a single ZTF image. The cadence is every 2 to 3 nights, and that is how we have already 1,500 images or so. Right? And then these numbers are really large, billions, something like that, and we start losing comprehension of large numbers. So I stopped updating them since January 2025. Another factor of 3, 4 is not going to matter much in most. But you can look at this PSF CAT science images, aperture CAT science sources, etc. aperture CAT. So what we have is about 2 billion sources that we have been observing, and large number of times. So you can do really lots of things. Even given that only a small fraction of them are variable, let's say 10% of them are variable. So 10% of 2 billion is 200 million. So you have that much of data to play with. Also, the good thing is that we have been making these public so everyone can access them. So not the latest observations, but once we process them after a few months, those become public also. So you have all of them. And here is a URL that allows you to get details of that, for instance. So this I mentioned about ZTF, but Rubin is deep. It starts at 24th magnitude. And when you co-add all the images of LSST, you'll be able to get to 27th mag. The number of filters is also larger, U, G, RI, Z, and Y. So it covers a larger wavelength range, which is great, complementary. Roman will be space-based infrared. It's also deep. A single image, the longer images will go to 26th magnitude, right? It's already far, far deeper. And when you combine more of the Roman images, it will go a magnitude or two fainter than that. So we are really sampling a deeper space. And it'll have an amazing resolution of 0.11 arc seconds, right? So I always like to compare that with a test pixel, which is, I think, about 17 arc seconds. So about 300 ZTF pixels fit into a single test pixel. And about 100 Roman pixels fit into a single ZTF pixel. So about 25,000 Roman pixels will fit into a single test pixel. That is why with tests, we have difficulties in understanding if something is a binary star or not. So you have to use a parameter like the Rubin parameter to figure that out and so on. And then, of course, we'll combine these or use additional surveys like Gaia and Euclid with these to aid in the classification. So that's where all of these are being brought together. And then we also, of course, despite all this, there will be some objects that cannot be classified really well, and there will be citizen science projects with that. So one of the things that we currently have, which is not a citizen science project, but it's an outreach project called ZART. So here you see, you can scan that QR code if you wish. So here what we have been doing is that the latest transients that we have from ZTF, we have been putting that onto this game and people can catch those transients. It's like Pokemon Go, but for astronomy, and you can climb leaderboards and so on. But right now what we have is that different classes where people can catch those, but also we have two ambiguous classes where our classifiers are not confident in their classification. So then at some point we hope to bring in the human neural networks to help us classify those, where we'll be going along that.
Ashish, can I ask you a question?
Yes, go ahead.
You mentioned that the TESS, which is also space-based, had much poorer resolution compared to Roman. Why is that? Why is that so?
So, sorry, Roman has a higher resolution. TESS, the reason TESS is low resolution is the amount of sky, the volume of sky that is being looked at the same time is really large, right? Using only about 24 different positions of TESS, the entire north and south sky can be covered. Whereas with Roman, even if it is called a wide field survey, so for instance, a single Roman image is 100 times that of Hubble, but the area that it covers is only about 0.28 square degrees. So compare that with ZTF. So we will have to have something like, again, 200 Roman scans, Roman footprints to cover a single ZTF field. And ZTF field is also much smaller than what TESS covers. So it is the different things, different science goals that you have in mind that determine how these things are operating. And that's why they are very different from each other.
Okay. Another request. You had put in a website address when one of your slides. If you could, simultaneously or afterwards put in the chat box, I can test those things out. Huh?
Yeah,
thanks.
We can do that. Yeah, thanks. All right. So here is one possible workflow that would work. So Rubin, because it goes to 24th magnitude in a single image, one can find very good transients with those kinds of objects that we have not seen before at all. And ZTF and other telescopes, their cadence allows for characterization. So for instance, if image is found, Rubin finds one transient, one can go to ZTF either up to the 20.5, 22 or 24th magnitude, and given the long history, see if it was seen in that before or not. And if it was seen, then one can characterize it. But if it was not seen, what is it? How we can use colors from other surveys to look at it will be useful. And that is where the machine learning comes in, the characterization of the fainter objects. Because no matter how much machine learning you do with ZTF at the 20.5 magnitude, once you start finding objects at 24th magnitude, you'll need to have some new training. And that's where the transfer learning part can come in. You can still have some program, some understanding at low confidence perhaps, which will classify based on what we have from ZTF. So you do need to train machine learning in that way with existing data like ZTF. So they're ready when the data from LSST is coming in full swing. And that is why all the brokers that are going to work with LSST were using ZTF data. They were getting trained on ZTF data, learning about the different algorithms, fine-tuning the algorithms, and trying to understand what the universe that we currently see is and what we are likely to expect after that. And then there are other characteristics, the scientific characteristics to keep in mind, of course, because Roman is infrared, it goes to about 2.54 microns, then it's going to reveal many dust-related characteristics. So it's going to take us into a different domain also. So even if you do a lot of training on optical data, not all of that will be transferable to Roman. So we'll need to do some transfer learning, additional transfer learning there as well. right? And then what one may want to do is do a lot of coordinating spectroscopy. So when you want to do follow-up, there are networks like the growth network that we use with ZTF, and Varun, who's sitting here, he's been spearheading that here from IIT Mumbai. So there'll be a lot of opportunities to do follow-up observations with different telescopes. LCOGT is another example where they have same size telescope, they have standardized that, and you can cover. So they have telescopes all around the globe. So one of the statements that is made is that the sun never rises on that empire, because you can always find some telescope which can observe any given object at the time. And then again, transfer learning that I have been mentioning, that is something that we need to keep doing. So one of the important things when you do machine learning is the things that I've mentioned here. The interpretability is critical. There has to be fairness and trust that comes in, because when you have a machine learning algorithm, right, when you ask it a question, when you are doing inferencing, it will always give you an answer. How do you know whether the answer is right? And the way to know that is that you have training data sets where you can look for validation sets, etc. But also when the features that you're using, you can ask questions like which of those features are more important, which are those are more interesting for specific classes, but also build in these specific things related to which of the features are going to be helpful for these classes. And there are many different ways in which you can have that. So for tabular data, text data, image data, there'll be different areas, but also you can do local versus global understanding of how the data are. So for instance, if you're using gradient based methods, then is it the early layers that seem to be more contributing more, or the later layers? So there are other things like GradCam, etc., that look at that. And then there are many ML tools that are being developed. Those often come from the large data sets that are available to the companies like Microsoft, Google, and so on. So variational autoencoders. Earlier, the autoencoders, they would have pointwise relationships. So for instance, if you have images and text, then those would be matched. And then if you found something identical, then you could go back and do a one-to-one correlation. But with variational autoencoders, what you can be doing is that you can look at a bigger latent space. So you're not only looking at pointwise things, but also looking at wider areas. So that sample the entire space rather than individual points. Or the clip algorithm or transformers, many people have been using that already. And the interesting thing about transformers, though, is that once the large language models came in, their usage, the number of papers that you see with transformers have actually gone down. So some ideation has somewhat decreased, which is a bad sign. So we should make sure that even if we are using large language models, we are not replacing ideation with something like that. So that's something that we all, especially as academicians, we need to be careful about. And that will be again related to the trust part, because hallucinations are still rife in all the LLMs. All right, so brokers I mentioned earlier. ZTF is only about 10% of Rubin. And so it has benefited a lot from the LSST spurred funding. LSST, again, they had funding or have funding only for observations, whereas the classification part is left to the community. That is where the brokers came in, applied for those fundings, developed various things, and so on. And some of these brokers plan to stop processing ZTF streams once LSST starts fully. And that may not be a good thing, because we do need things to be at the brighter end as well as the fainter ends, right? In fact, newer surveys like Roman should be included in the alert processing. So that's one of the things that we are trying to do at Caltech. We have something called Boom that I'll mention later on, where we are extending what we have with ZTF to LSST, and we can do a combined processing, and we hope to extend that to Roman also, because especially when you have information from all these surveys together, you can learn that much more. So there are these groups like the transients and variables group, variable sources group in LSST, or the ISSC, which is the computational part. So there, some of the tasks that are being given out is encouraging brokers to be modular. That should be true with all code that you write, right? Meaning if your code is not modular, then there are likely to be issues down the line with that. And encourage schema matching between these. So if there is a way you can do classifications for LSST, then by making small changes, there should be ways to do the same thing with Roman. Of course, funding is a different issue. Many times, if you are funded to do something with LSST, even if the volume is only going to increase by, say, 15%, you may not be able to do the classification using the funding stream that you have. So you have to be wary of that. But again, if the code is modular and public, then someone else could pick it up and do that, so that the science itself benefits. All right, Boom is what I mentioned earlier. This is where we are currently going. It's started functioning recently. This is next generation alert brokering in the ZTF Rubin era. So one of the things, again, I mentioned before is that different groups care about different subsets, and how do you take that into consideration? So what we have is that ZTF has the images which go to IPAC, which is part of Caltech, which releases alerts. Those alerts are consumed by brokers, and from those brokers using marshals, candidates are found, and then classification is done, which is then released to the community. Many of these aspects can be automated. In fact, many of them have been automated, at least for subsets of science. But again, there are anomalies and so on where one has to have human on the loop, if not in the loop. The slight difference between in the loop and on the loop, when you talk about in the loop, the human is in between and can be a bottleneck, whereas on the loop means that the loop is happening automatically, but you have ways of validating some of them. And so on the loop is a technique that is being used more and more to make sure automation continues. And so here what we have is that Kowalski, which is what we have been using for a long time, it receives alerts from ZTF, then there's spatial cross-matching with archival catalogs and other streams. Again, making sure that you use archival data is very critical. It's not as if when you're doing transient science, the archival data cannot be used. That becomes very critical in this case. And then you can update the full light curve for each object. And then you can run ML models on the alerts. So BTS bot is one of our examples for the bright supernovae. And in fact, one of the automated setups that we were able to execute some time back is that with the 1.2 meter telescope, ZTF gets data. The data comes to IPAC, it gets processed. We have alerts. The alerts are then broadcast. From that, a subset of alerts, which are supernovae, can be chosen and sent to a slightly bigger telescope, 1.5 meter telescope, where there is a low resolution spectrograph, which then takes spectra automatically, which are classified automatically. And in fact, we were also able to send a telegram from that automatically. So all this loop can be now done, and more of that needs to be done. Again, it is possible for a subset of objects which we understand better, but at least for those objects, we should definitely be encouraging more and more of that so that we can get to other science more easily.
Ashish, can I ask, is there a reference for the BTS bot?
Yes, I can provide that as well.
Okay, thanks.
So users have different user-defined filters. So for instance, if you are interested in asteroids, then you may be interested in movement that is shown. If you're interested in supernovae, then you are interested in something that was not seen before, has become brighter and then faded away. If you are interested in flares, you are interested in something similar, but the rise time may be faster and it dies quicker also, unlike a supernova, which will die slowly. So those things will define various filters for you, which will allow you to look for objects. And then those filters allow you to characterize, and that is what will bring me later on to the gap analysis that I'll mention. And so again, some more details of the boom part about automation and so on. I already mentioned that. Here are some technical details. There is Kafka topic reader. There is some in-memory storage from database, which goes back and forth with this machine learning workers, filter workers, etc. And then there's a Kafka cluster from which it goes to marshals and others. So there are a lot of, again, modularity is there. And that is why when you have different parts of it, which you can switch in and switch out easily when you are interested in slightly different analysis of the data. Again, multi-survey support, that is why BOOM was developed. So going from just ZTF to ZTF plus LSST, and hopefully later also Roman, and bringing in other things. So here are some details of that we have. Again, we can go into more detail later on if we need. But again, one of the critical things is standardizations of the schemas is critical. So if you're speaking one language for one survey and some other language for another survey, then combining those is really difficult. So those standardization aspects are what we really need to make sure that they exist. And that's something that all brokers should be doing. If you are involved in some development, again, try to standardize, try to make sure that it's modular and so on, right? And there are many choices that one needs to make in these different cases also. So now coming to the Roman part, the alerts that we are developing, again, we are developing on the same lines roughly as ZTF and LSST. But again, what happens is that as the depth changes, as the number of alerts changes, how we go about doing that can change a little bit, so long as we keep in mind, again, the standardization of schema that will be important. So this is still work in development. These are slides from Ben Rashon. And again, as time goes on, we'll be able to figure out where we'll be reaching with Roman. So again, here again, we are going to use external catalogs and archives. PanSTARRS was a perfect match for ZTF. Where what we could do is that we could look at the PanSTARRS data and look for slightly fainter images that PanSTARRS had, so that when we had corresponding images from ZTF, be able to say whether what we are seeing a transient, if it was already seen in PanSTARRS, then maybe it's less interesting. Similarly, what needs to be done with Roman is see if we can co-add images and get to some depth. But again, given that a single image will reach 26 magnitude, that's not going to be easy. But even if we can reach some fraction of that, then we'll be able to eliminate false positives at that level. So Euclid data, we should have DR1 possibly by October 2026. It's not going to be before March 2026. Hopefully by October 2026, we'll have that. And that's about the time when Roman is going to be launched. So day one of Roman, hopefully we'll have some Euclid data there. And the Rubin DR1 should be there by about January 2027 or so. It's already doing commissioning data, so the 1 year data will be available. So again, LSST is optical, Roman is not optical, but we'll be able to get some idea of what kind of sources that we have there as well, right? And the coverage information, we still don't have enough of that either for LSST during the first year release or with Euclid also. That should be forthcoming soon. One of the things that happens is that the large number of alerts that we may have, it may not be possible to hold all of them in memory, and there'll be some loss that will be happening, and how we handle that is something being decided with Roman as well. The alert stream may have to be split by time because Roman will be continuously observing. So you'll have certain times when you observe something and then you go and observe something else, which ones that you have, and look at that later. Yeah.
So what is the rate of alerts that you are expecting?
We don't know yet. So that's something that's being calculated. And it won't be as much as Rubin. It may be as many as ZTF. But again,
because I mean,
it's a tiny field, right? But
right, so
yeah, it's the funding, mainly funding, right? So the funding that is available for the individual groups and the processing that needs to be done. Again, the turnaround time for alerts is less than, I don't remember the exact number. So the level 1 and level 2 processing, which will come from Space Telescope, the maximum time that they will take is 1 day, which is already too long, but that's the upper limit. And they are hoping to bring it to as little as a couple of hours, for instance, or even less than that. And after that, what Rapid has promised is that the alerts will be released ASAP. And if that ASAP needs to be done, then you may need to keep on shifting things. If more funding becomes available, yes, that should be the easiest thing to do, really, because more memory. And maybe in a year's time, we'll have more things. But again, when the proofing is being done, it's done with some hardware that is already in place right now. It's not easy to swap in and out hardware. So again, it's being done at IPAC, so we'll know. So that's the current statement. We are hoping that that is not true. We'll be able to do much better than that, right? And right now, also, there's no plan for an alert database. Again, that is something that hopefully the community could do. That's what, again, the standard lines that the funding is for this, we'll do this, maybe not that. But again, it should be an easy thing to do. And maybe that is one area where if there are people here who want to step in. The good thing with Roman, again, like most newer NASA facilities, is that all the data will be public from day one, right? There's no proprietary time. So again, whatever science you want to do, if there are ways in which you can develop some tools and so on and feed it back. So I'll mention some links to various groups from Roman. Again, it'll be great if people here are interested in that and can join and contribute and so on.
Can I ask another one before you leave the topic?
Oh, sure. Yeah.
Yeah. So you mentioned multi-catalog correspondence and correspondence. Just the previous slide. Now, the information that you are showing are primarily from optical bands. Is there any effort or any something on available that compares catalogs from not just optical but also from other wave?
Yeah. So we'll be using that. And in fact, infrared will be more useful for Roman. And we do have certain things starting way back from 2 mass, for instance, which was much brighter upper limits. But everything that is available will be put in, and we'll be trying to use that.
Including X-rays and radio.
Yes. Yeah. And that makes it far more difficult. It's not a trivial problem. So it'll be as much as is feasible with the existing funding, and combining all the data with all their temporal exposures and so on may not be feasible. But if there are combined snapshots, and from those snapshots object catalogs that have been generated, those are the ones that would be used at the 0th level rather than say.
So therefore the snapshots of specific objects or specific regions
Right.
will be of importance.
Yeah, yeah. Mhm.
Okay.
And again, that is one area where there is more scope for people who are interested in doing things to do so. All right, so let me come to a little bit with machine learning with Roman that is already being tried. So there's this Open Universe 2024 catalog that's been made for Roman and Rubin, and that's the one that's being used. There's another one called RimTimSim, which uses some variable sources, and we're trying to combine the two because so far what we have developed is on the Open Universe 2024, which has only extragalactic transients, which makes it slightly difficult because then it's easy to train your algorithms for supernovae, maybe kilonovae, maybe tidal disruption events, but possibly not for standard variable objects. And initially, variable objects is what will really be important, because when you look at 26th magnitude, then you'll find variable objects that you've never seen before, and it'll look like maybe transients. You have not seen them before, the first thing. So we need to have that in place, and we have only 1 year to get there, but that's what we are pushing through. So every quarter we meet as a Roman group and make advances. So this next quarterly is in Pasadena in December, where we'll be setting up some hackathon for all Roman users. Well, some of these things, post photometry, co-additions, as well as real bogus will be coming into picture. And so detecting transients, separating the real from bogus is important, and classifying real transients from light curves is what will be coming into picture. The finding transients, we're also trying out some with pure machine learning. So standard techniques are where you use Zogi or SFFT, where there's an image differencing that is done. But with machine learning, there would be ways of detecting the transients directly by comparing the two images. So we have shown that in a basic way with CRTS images, but that's what we are now also trying to implement with Roman. And so let me skip this part. I think I mentioned all of this. And so this is the method that can be used with CNNs to directly detect transients we have. So again, these are simulated images, but even if they're simulated images, these are fairly detailed. The total amount of data that are there is 400 terabytes. And all of that is publicly available on AWS. So again, if you're interested in trying out some of the machine learning methodology, you can feel free to do that. If you have something, a technique that no one else has used, and if you want to show that, that's the perfect thing. So this includes, for instance, images, truth tables, and everything. Again, right now for extragalactic objects, at Caltech, we have been starting to inject variable sources into that also with specific cadences. So that should become available in the next few months as well. So these are some of the transients that you can see. There are these classes: supernova type 1A, 1AX, type 2, 1B, 1C, etc. And then there are some TDs, etc. But the other numbers are fairly small. Again, we want to combine these with the variable sources that we have in there. And again, detection pipeline. Looking at the time, I'm going to move forward a little bit. So again, examples for bogus, again, in simulated data, you find all kinds of things. And one of the important things to do would be to understand how these would look and be able to separate that. But again, what we need to be prepared for are surprises when we go from simulated data to real data. There will be surprises. And so the machine learning methodology we are building will be such that by taking a small amount of real data combined with the older training that we have, we can do quick retraining so that we start understanding the features, the characteristics of the real data as well. So here are examples of some true positives and true negatives, and some of the real objects can be really faint, especially if these are extragalactic objects that are supernovae that are sitting on top of a galaxy. It may not be easy to find those, right? And initially we had used a small number, but that number with the Open Universe catalog has been increasing rapidly. And so there's a big variety of bogus events that we see even in the simulated data, right? And so you can see things, of course, we are removing single pixel things which would look like cosmic rays, but there are even several things with age on galaxies and spikes and various kinds of things. So one of the early things that we are trying to do is also cluster the different bogus events. So try to understand what those are. And so once you start understanding in a large parameter space where these lie, then it will be easier to start removing those. Because initially what you have is that for every real, we have more than 1,000 bogus. And what that means is that most of a classifier, then if it simply calls everything a bogus, it's going to have a high accuracy. There will be other parameters that you can use, of course, but that's the thing that we have. If the classes are not balanced, the real and bogus, then there's the danger that the classifier will not be easy to train. So initially, we definitely want to make sure that we move away from that. So the ongoing work for that is better augmentation, try to make sure that we have lots of different things, experimenting with different layers and image sizes. So again, we don't want to be able to detect objects and then say whether it's a real or bogus, but we want to be able to take an entire image and be able to say what it is. And again, as I said, even if the field of view is tiny, 0.28 square degrees, because the resolution of the pixel, 0.11 arc second, we have enough number of pixels in there. So we will have the transients that are scattered around the entire area. And so again, as I mentioned, what we'll be using is both the VAs and transformers in that coming in. Right. And the clustering that we are doing is again using these kinds of variational autoencoders. This is a variety of different kinds of bogus that we have. So using these autoencoders, one can easily characterize those and start understanding their nature so that we can handle them more effectively. And then that is when the real interesting part will start. So once you have separated the reals from the bogus, it is then that you can try to understand what the different kinds of reals are. And that's where the training of ML algorithms, separate set of ML algorithms comes into picture. And again, we'll be using various things like RNNs, LSTMs, and GRUs. DMDT method, I was talking yesterday, some people here have already used it. That is the method that we have used to characterize light curves with a structure function. So the DM stands for the delta magnitude, DT for the delta T. So for every pair of observations in a time series, you create a histogram and populate that histogram with that. Then you provide that as input to a CNN to do that. Then there will be the standard feature-based classification also. So given a time series, you can get large number of statistical features, mean, median, skew, kurtosis, various kinds of moments, etc. User-defined things for specific classes. And then in that large dimensional space, you can do classifications. And then combinations of these also using color information, use other kinds of data when those are available, etc. So here are some of the models that we have already tried, and many of them do not get great results, again, primarily because we still have a large number of bogus events. But now we are coming into this rotational invariant CNNs where we can get large accuracy, but also large precision, but still a low recall. We have managed to move to 0.72 in some limited cases. But again, what this means is that you are able to get most reals depending on what threshold you have been able to put. Again, in our machine learning models, we'll be providing the threshold values. So users can decide where they want to, whether they want as many reals as possible, even when they're going to get a large number of bogus, or they want to be in a space where they don't want any bogus, even if they miss a large number of reals. Then you can determine your follow-up based on that in a specific way. And this is just a precision threshold curve for that, where this indicates what is it that you're going to be missing with different levels of these different thresholds. And again, the interpretability is paramount. So we will have things like GradCam in that. So we understand, given a particular object, what are the pixels in it that are defining for us the realness or the bogusness of that particular object. And again, that will be transferable to other data sets. So we can keep on using that in the long run. Yeah, sorry? Sorry? How elaborate? How reliable? It's fairly reliable, actually. Yeah. So with GradCam, you start. So what happens again? That's where the human on the loop comes into picture. So you see a large number of examples. You also use that along with clustering with t-SNE or UMAP. And then you start looking at various examples to understand the coverage of the parameter space that those have. And you can start eliminating certain regions and so on. So that's fairly reasonable. So there are, of course, still very large number of issues. The data sets are still unbalanced. The light curves are fairly sparse. There are missing types, variables, as I mentioned. There are no AGNs in there, which are going to be fairly large, given that we'll be going to 26th magnitude. Even with LSST, we'll be going to 24th magnitude. So AGNs that we have not seen before are going to pop up all the time. So they need to be there. Solar system objects, there are different groups that are looking at that, of course. But again, those will be quite large. And then exoplanets, microlensing. So there is a separate survey with Roman for microlensing, and that'll be, again, right now in the simulations, we don't have that. A different group is working on that, which we want to combine. So we have a group called the STRIDE group for Roman time domain. And again, it's a group that's open for everyone to join, where people from different sciences will be combining their expertise to see how they can help each other in different ways. So again, this is how the surveys are going to look. These are the three things: the high latitude wide area survey, the high latitude time domain survey, and the galactic bulge time domain survey. These are the three primary surveys that we'll be doing with Roman. And what I'm going to mention, so these are the different science things that can be done with it. Again, just an image, not from Roman, obviously, we don't have that. But what I wanted to show are these different groups that we have. So these are the working groups that all report to Roman itself. We have got calibration software, simulations, again, primarily things that are required in the analysis. This is the time domain group that mentioned. It's a overall thing, STRIDE, where we try to bring in expertise from different groups. But then again, this is the science collaborations. These are independent and community led. And again, these are also fully open. You have got Milky Way and stellar astrophysics, exoplanets, nearby galaxies and quasars, explosive transients, and cosmology. Again, because Roman data is open to everyone, everyone is open to join these. So you can, again, scan those QR codes in order to find out. Again, I'll leave these slides here so people can refer to those later on as well. So we can join any of these and be able to contribute to Roman, but also benefit from what's going on. Many times, though the data are open, you'll get understanding the intricacies of the data taking is quite critical, because that is what tells you what are the shortcomings of certain things, what are the lacunae in certain things, also what are the small bits of details that you'll miss if you're simply consuming data once it's available. So during these groups, when things are being discussed, how are the exposures? For instance, for the galactic part, the exposures are about 60 seconds. But for the high galactic latitude, the exposures go up to 3,600 seconds. So when you have so deep exposures, what are the changes that come about? What are the things that you need to understand? Those are the things it's better to understand when things are being developed, because you do understand the intricacies. So getting involved in some of these will be quite useful for many people. And then these are the various working groups, as I've mentioned. To sign up, this is the link here. Again, I'll make sure that this gets posted later, so you can go to that and take a look at that. And the meetings of the different groups, the frequency is not very high. And initially, you can just lurk there, understand what's going on, and then get involved later on as well. STRIDE, for instance, meets first Friday of every month. So at least 1 hour per month. We do have intermediate meetings once in a while, but that's the kind of frequency initially. And then more ways of getting involved in the science collaboration. All right, so let me move to the gap analysis part in the last few minutes. And this is something with ZTF that we have been doing. So what you see here is that in a full night, if we have these number of alerts, and then different groups are interested in different things. So a small fraction of those will be real, some of them will be not real. And then the reals also can be defined through positive subtraction versus negative subtraction. What I mean is that an object could get brighter than the underlying comparison image that you have. And so that would mean that's a positive subtraction, but you could also have something of a dip. So an object becomes much fainter, and that would be a negative subtraction. We do it both ways. So some would be one way and some would be the other way. And then a large number of these positive subtractions, or small number, can be asteroids, known asteroids. There will be unknown asteroids also. And then some of those would not be asteroids. And then what you will do is that, so ZTF gets of the order of 100,000 million kind of transients in a night, and then you do real bogus comparison. And obviously, the science groups cannot be looking at all of them. So after you do this filtering, they add their own filters, and then it's a tiny number that get looked at. So most of the transients just get thrown to the floor, right? And many of them may be fairly common ones, not interesting ones, perhaps from your own science, but there is a lot of interesting science in there. And that is what we are trying to understand from here. And so these are the ones that are not filtered, and then these are asteroids, and then these are further filtered, etc. So it's again of the order of 100 to 1,000 transients that get really looked at. So what are the other ones? We started looking at these, and then there's Disney, various variables that are mapped by size and colors. Once you start looking at those, so you take all the filters by all the groups and start with all alerts on one side, and then start comparing the two. What is it that's being missing? And then you can start looking at them in more ways. And here, these drop downs allow you to select whichever science that you may want to, or combine multiple science, etc. And then what you have here is that for each of the parameter, you can start moving these sliders on the side so that the other sliders can light up to see when you choose, say, supernovae, are there other science teams that are also picking supernovae? For instance, how much is there an overlap between TD and supernovae? Or if you are looking at flares, are there certain TDs that are coming up as flares? And then if there are a large number of alerts that initially seemed like one of these, then why is it that they're not being picked? So those are the kinds of insights that you can look through these visualizations that are completely interactive, because you can use all these sliders and so on. So a single slide does not do justice to what the tool does when you can look at it in an interactive fashion. And then you can look at, so for instance, stat across fields of interest for all data in dark gray compared to single filter in pale blue. So you have a single, by filter here mean filter from a group trying to identify their own objects versus all the filters from all the groups. So what is the subset that they're being able to pick? That is what we are looking at here. And then we can again look at it as a function of time, as a function of moon phase, as a function of time of the year, etc., looking at the gaps. And so again, distribution of alerts across filters in 96 different nights. So on some nights, there seem to be more supernovae for whatever reason. There shouldn't be, right? Meaning it should be distributed well. So what are the other causes? What are the other factors that come into picture that give rise to something like that is what one can look at. And these kinds of analysis are important because especially when you're going to be looking at 10 million transients, you're using a large number of resources also. So if you can, if finally you're going to look at only 1,000 of them, are there ways to get to those thousands as early as possible? That will reduce a lot of things. But also, if no one is looking at that, are these mainly anomalies? Are these parts of science that we are not looking at all? Those are the questions that we were interested in. So it's still a work in progress, but we have made some good progress trying to understand what it is that is out there. So again, filter IDs. And then when you start looking at correlations for different classes, you do find that many groups. So again, this is part of the modularity, but again, laziness of human beings. So one group defines that something is an asteroid and everyone tries to use the same definition elsewhere, even if their interest could be slightly different from that. So that's where we can see how the large number of filters get correlated with each other. And there are multiple options in there that they can look at. So that's something that can go on. So this is what brings me back to the brokers, because the brokers are trying to do exactly this, right? The brokers want to do early classification of these objects. And by the way, this is an auto-generated slide. This is not from actual brokers. This was ChatGPT at work. So I gave ChatGPT a prompt about how different brokers work and what they do, what are the features that they should have, etc. And so these are a few different brokers that have been working with ZTF and will be working with LSST. What are the different types of features that they need to have with those? And so comparing these different brokers is something that is of importance, because as we move forward, trying to combine data from not just ZTF, Rubin, and Roman, but also trying to bring in other things like Alak was asking about X-ray and radio and so on. We want to be wary of the different features that we can be using, try to make things better for ourselves, try to make sure that the false positives are as few as possible as we go in with those. And so we start defining the desired features with each of those brokers, which brokers have these, which don't have that, and how we can use them in a complementary matter rather than like a competitive matter between the different brokers. And so I'm going to stop with this summary. We have got about 8 minutes left in the hour. There are some slides that I have for cancer. I won't go into that, but if there are questions, we can think about that. So what I would say is that to take advantage of complementarity of these different surveys, we need to have adaptive brokers. That's quite critical. And there are many possible methodologies that we can use for that to bring those about. These will allow population level analysis, not only the individual outlier anomaly kind of thing, but population level analysis, which is what we like to do. So that can also drive discovery of new classes as well as subclasses. And lessons from ZTF suggest that trimming of alerts early is likely to help with this brokering, understanding of more of science that we can be doing with that. And of course, machine learning classification and science that we can be doing with that also. So let me stop with that, and I'll be happy to take any questions.
You talked about training on the brighter objects, and as we go down to lower mags, you need transfer learning to allow for, because the noise profile itself has more noise. So how do you do that while ensuring that? I mean, of course, you'll fix certain layers and keep the others flexible to allow for that for the incorporation of that. But as the noise profile keeps getting worse, how do you decide?
So one of the easiest things that you can do is through some holdout. So even when you have some only brighter data, it has a range of magnitudes. So if you train it on the brightest among those and see how it performs for the fainter ones, at least for that brightness range, you understand that it's going to work reasonably well. And then you can keep on extending
So
that.
it's basically adaptive,
it can be adaptive, but that is not a guarantee that it will work for further fainter, because if you are going to reach populations that were not seen in this data, or wavelengths that you are not covered in this data, but that can be the least that you can do. And then you can start simulating based on the knowledge, the physical knowledge that you may have, to try to extend that.
Sure.
Ashish, I was wondering if you could comment on the computational and storage requirements of these efforts and how they are being met.
Yeah. So again, as I said, the Open Universe 24, the simulated data are 400 terabytes. So those are the kinds of numbers that we're looking at with high resolution data and with intermediate projects. That's something that's going to be really tricky. So you may not be able to hold everything in memory. You may not be able to have everything be looked at. And so periodic compilation of the data, co-addition of the data, those are the products that will be saved and reused. Rubin, for instance, is going to release annual releases of that, right? So intermediate ones won't be. And then if suppose you either discover a bug or something new technique that you want to use, and if you want to rerun on all the old data, that's something that's going to be really difficult, right? There is some scope for doing that in the funding that is there, but only a limited scope. So it's going to be tough, right? I mean, despite what we have, it's not hard in itself, but it's tough primarily because of the funding that's available. Right? Because the disks are getting bigger, GPUs are getting faster. So technicality is not a problem, right? Meaning it's more sociology, it's more the politics that's involved in that.
Thanks, Ashish. So I had a question. You mentioned that you're exploring methods without taking the difference image for the transient detection. So what is the motivation for that? Is differencing somehow suspect is causing some information loss? Why are you exploring that option of trying?
So with many machine learning algorithms, what happens is that if the algorithm works well, once the training has happened, then inferencing and application of that is essentially in zero time, right? So if you develop a method which can do image subtraction so that it magically tells you where the transients are, when you have a new set of images, for each image, you are going to take almost no time. Whereas if you are doing actual subtraction, that is an expensive procedure. So that is the thing that we can aim to have an advantage in when you do machine learning based
computation.
Right.
Thanks.
Are there any other questions?
I have one on the web.
Please go ahead.
Okay. So, Ashish, I'm trying to formulate the question as I'm asking you. You talked about bogus versus real events. Real, real events or real data. Now, the 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 relative ratio must become more problematic as you approach the threshold of the images that you're taking. So, whereas this may be slightly better if you're at the brighter end away from the threshold. So, um, does that is that taken into account while deciding which one is real, which one is bogus?
Yes, it is. So what you are describing is related to the noise in the image, but the bogus that we are describing can also be dependent on the way the processing itself is done. So for instance, it is the PSF matching that may not have been done well, in which case there can be residuals that are left, or there is slight whatever that happens in terms of, say, the distortion or reflections that may exist. So it is those bogus that can be more difficult, and those won't follow the kind of law that you're describing.
And if you introduce, let's say, test stars of various magnitudes, close to threshold as well as slightly away from on the brighter side, on the test on the brighter side, do these techniques help you to get rid of more of the bogus things?
Yeah, so those are the kinds of things that we are doing right now. And what you have to be sure is that not only the test stars or injected stars are of different magnitude ranges, but also different colors. And when you want to look for false supernovae, then also injected on different parts of the galaxy, etc. Yes, those are the kinds of things that are going to be done next now.
Okay. And yet another question, related but somewhat different. What can, for example, a set of brokers and marshals devised for another band can learn from this analysis of bogus versus real data?
Yeah, so there are some kinds of bogus versus real that would be common across wavelengths as well as depths, etc. But there would be more that are different when you change wavelengths as well as depths. So you can learn a limited amount from those. Those would be the starting points. But ideally, you will want new examples from your target wavelength as well as target depth to be better at distinguishing the real and bogus.
Mm-hmm.
Yeah, it is a challenge.
Yeah.
Not real. Yeah.
Okay, and if possible, I would like to, if there is going to be a link to your talk or especially the references that you had
Yeah.
out, that would be really
So
appreciated.
I have provided the PDF to Parag here, and it can be shared or kept wherever, so that will be available.
Oh, thanks. I enjoyed your talk.
Yes, thank you. At the end, there are also some cancer slides, which will also be in that, so you can take a look at that, and happy to talk about it later.
Uh, I hope it will be part of the asset so that I can also see it.
Yeah.
Sure. Okay. So can you take just 5 minutes to give us overview of the medical things which you are doing?
Okay, I can do that, meaning if people are still patient. Yeah, 5 minutes then. Okay. So what we have at JPL is Early Detection Research Network for early detection of cancer. And JPL, if you don't know, is in Pasadena. It is managed by Caltech. It predates NASA, so it formed before NASA formed. So it's a very interesting, strange place because it's a federal agency and yet governed by this private institution. And what many people don't know is that it also has cancer data. So I've been working with that for a long time. And you can see here some distribution of what different cancers data that we have and some different kinds of data sets that we have there. And we have this, as I mentioned, the Center for Data-Driven Discovery, for which I work. So that's the one that's been collaborating with JPL to look at these. And what we have again is this LabCast biomarker data-driven ecosystem. So these ecosystems, whether for cancer or for astronomy, are in some way not very different from each other. So you've got incoming data, then you do various kinds of analysis for that. And then there are the outputs that you have, which analysis teams look at, etc. So primarily here we are detecting cancers rather than detecting galaxies or other kinds of objects, so somewhat parallel in that sense. Here is something related to lung cancer data, for instance, that what we had is a set of tumors, benign or actual cancers, and we had a few radiologists look at those, and then there was a training that the radiologists went through. So they had been asked a series of questions, and then they were asked again the same set of questions for a different set of images with some overlap from the earlier images, and how do they compare? And this is where AI ML can come into picture, not so much to replace the radiologist, but to see how we can collaborate with the radiologist. So together we can get to better things. So train the radiologist and also learn from the radiologist in this. So this is essentially like a digital twin in this case, with explanations and again interpretations. And this is where what can happen is that you can start getting into areas which were not looked at before. So looking at the margins of the cancers can be an interesting and important thing. And the contrast there can often be very low. So this is where machine learning algorithms can come in and start doing better than radiologists, or try to teach radiologists a little bit about that. Here, for instance, as you can see from the confusion matrix, we're getting reasonably good classification for these margins here. Right. Or for breast cancer data sets, we have some completely publicly available data sets as part of the EDRN, some 2D data sets as well as 3D data sets. And here one can use standard convolutional neural networks to start detecting cancers as well as start classifying them in different ways. This in collaboration with Dr. John Hein and Fowler of Moffitt, for instance. And one can do segmentation with these. So you have a set of 2D images which form a 3D data cube. And once you have these segmentation, what you can do is that you can also build a 3D feature set from that quite easily. You start with, for instance, mammogram images, segmentation model, feature extracted, feature selection, and then you can get to the stage classifier. So you can try to understand what stage that particular cancer is also at. And this was a animation where how you can build the 3D thing. So here it's a PDF, so we are not going to see that, but that's all right. And again, the same kinds of techniques that we use in astronomy for classification can be used here. So this one is for breast mass classification, how you can look for mass. And again, another parallel, we want to be very interpretable with it. So if you look at a mass of this kind, you can think the whole thing is something like a tumor if you're not in tune with how these things are. But much of that is calcification, so not really tumor. And then when you have these things, your earlier question about how reliable these methods are, so it's able to point out that, okay, this is the area that is really corresponding to what one should be looking at. And that turns out to be right in this case. And so here, what one can do similarly for transfer learning is that there are two different views. One view can be from the top and one can be from the side. And one can train on one, and it's essentially the same data, right? So you can train on one and see how it performs on the other. So MLO on MLO versus MLO training here and tested on CC, etc. So how the different AUCs can work when you look at these different things. And within that, again, you can try to bring in the temporal data, the longitudinal data. So as if you have early detection, then what that means is that if a patient comes in at, say, stage 3, but if in their history you also have data from when the cancer was not detected, how are those images different? Can we start looking at those images and see if we can find the cancer, etc.? So that's the kind of thing that can be done. Okay, those are the things that I had for that. Fungi, I did not prepare slides. I'm happy to talk to you later on, but 5 minutes, we got 5 minutes.
Any questions on this particular part of data analysis applied in different fields of science, which of course is also by testing things. Otherwise, you're all welcome to please join for the tea. Please join in thanking again for our wonderful lecture.